Welcome to the video on integral calculus. You may find this hard to believe, and you certainly will if you've seen my video on differential calculus, but integral calculus is perhaps even cooler than differential calculus. So we'll start with the idea of an integral, and we've hinted at that. An integral is the area underneath a curve, but we're going to do this from a physics perspective. So I'll present to you a typical graph that you may see in a physics problem where you've got time and you've got something that's changing. In principle, it could be changing as a function of time. So here's velocity. So I want you to consider something that has a velocity. Let's say that it's a badger, and this badger has a velocity given right here. It's going 10 meters per second, and it maintains that velocity for 4 seconds. 10 meters per second for 4 seconds. And I promise you that you can very easily find how far that badger has gone during that time. You can develop a physics equation for it, or you can look at the area under that curve. Let's look at that. If we know the area is, what is it for a rectangle? Base times height. The base, well, the base is 4 seconds, and the height is 10 meters per second. If we multiply 4 seconds by 10 meters per second, we get 40. And what are the units? We've got seconds times meters divided by seconds, so we're going to be left with 40 meters. Okay, so that's how far the badger has gone. I'm not sure if you believe me, though. This is a distance, and I'm telling you that that's how far the badger has gone. But maybe we could also look on the physics side of things, and we could say if, well, let's see, I know that delta x is initial velocity times time plus 1/2 acceleration times time squared. And because the velocity is constant, 10 meters per second, there's no acceleration. A equals 0 here. So we can say that delta x is the initial velocity times the time in this case, which is, well, the initial velocity was 10 meters per second. And we're going to multiply that by the time, which was 4 seconds. And you know that multiplication is commutative, so this is exactly the same problem. We find it to be 40 meters. Okay, interesting. Just a hint so far. But let's do a slightly more complicated problem with integral calculus for physics. We'll say that we've got another graph of velocity as a function of time, and here the velocity starts at 0 and it increases to some final velocity, and this is happening over 3 seconds. And we're going to say that the velocity of a turnip is, let's see, the velocity final is going to be 4 meters per second. I'm going to write it down here. 4 meters per second, and that happens over a 3-second period. So first, I'd like to do it the physics way, and that says that delta x, we can use this equation. We know that it's 1/2 the initial velocity plus the final velocity, and then we'll multiply that by the time. So that says that we've got to do 1/2 times 0 plus 4 meters per second, and we'll multiply that by the time over which this happened, which was 3 seconds. Do all this multiplication together, and we get 6 meters as the total distance. So we got 6 meters as how far this turnip went. Interestingly enough, let's investigate the area underneath that curve. If I wanted to find the area, I would point out to you that area of a triangle is 1/2 base times height. And that's going to be 1/2, let's see, the base is 3 seconds, and the height, well, the height is 4 meters per second. If we multiply 1/2 times, oh shoot, 6, and the units are meters. This is also interesting. And for a final problem that really, I think, drives this point home, we get just slightly more complicated. So let's take a final graph of velocity as a function of time. I'll give you some initial velocity up to some final velocity, and well, let's say that this is 2 meters per second is the initial velocity, and the final velocity is 3 meters per second. That's that value right there. And I guess this entire thing happens over 8 seconds. So if we're trying to find delta x, again, we know that delta x is 1/2 the, well, it's 1/2 the base, what 1/2 initial velocity plus final velocity, and that's equal to, let's see, 1/2, oh, times time, of course, and that's equal to 1/2 times the initial velocity is 2 meters per second. The final velocity is 3 meters per second, and then we have to multiply by time. Put all that stuff together. Of course, it's not time anymore, it's 8 seconds. If we multiply all that by 8 seconds, this is 5. We're going to multiply it by 8 to get 40. We're going to divide it by 2 to get 20, and the units will be meters because it's the distance traveled, of course. But let's look at the area here. You see a quick way to do the area? I'll let you think about that for a moment. Yep, me too. Let's take out the brown. We'll take the area here, we'll call that area 1, and this guy will be area 2. So area 1, area equals area 1 plus area 2, and area 1 will be 1/2 the base, and on both of these, the base is going to be 8 seconds. So I'm going to do 1/2 the base times the height. In area 1, the height is just 1 meter per second, and then we have to add to that the area in 2, which is base times height, which will be 8 seconds times 2 meters per second. We put all this stuff together, we're going to get from this term 4 meters, and from this term 8 times 2, 16 meters, leading us to 20 meters. It turns out, I mean, this is hardly exactly justified, but it's certainly motivated to say that the area under the curve is really strongly related to the distance that's traveled. So we can write ourselves some maxims here, and that is area under a velocity versus time graph is displacement. Actually is the same thing as the displacement. Curiously enough, area under an acceleration versus time graph. You want to guess that? You want to guess what that is? Go ahead. It is something. Now I'll remind you that if we write x as a function of t and we differentiate that, we get velocity as a function of t. If we differentiate, we go that way. Do you remember, if we differentiate it again, what function is the result as a function of time? It's acceleration. So they kind of, it's rather interesting to see that if we go this direction, then this is called integrating. And if we go this direction, then that's again called integrating. So the area under an acceleration versus time graph is velocity. In fact, it's change in velocity. There's something very interesting happening with initial conditions. I haven't said anything about the initial conditions in x or the initial conditions in v, so we'll have to look at that in just a little bit. So.
Yup. Sorry.
Yeah, come on in. If I just draw graphs like this doesn't help you understand what's going on. I need to put something on these axes. So let's go back to our turnip thrown up into the air. It goes like that, and then we know that its velocity is positive, and it becomes 0, and it then goes negative. So it's 0 right here, positive at the beginning, and becomes very, very negative. And we can look at the slope of the velocity graph and see that the velocity graph is continuously decreasing, leading to an acceleration that's negative. And if this is truly a turnip, this is probably negative 9.81 meters per second squared. All right. Now, there's one more thing that I want to do about differentiation and integration, kind of to put it all together. I want to make the following statement. If you've got some function, let's say that position maybe depends on time, and if you integrate this, here's the way that we do integration. I'll explain what it is, why it is this soon. This is a large S, an elongated S for integration. And this dt, remember the d from derivatives, it's the same d that you've been used to. This dt says integrate over time. So this is a function position that depends on time. Obviously, position depends on time in physics, and we are integrating that function over time. If I take this integral and then, remember what this means? This means differentiate it. So I'm taking x, I'm integrating it, and then I'm differentiating it. It turns out that I get exactly x back again. This means that integrals and derivatives are inverses of each other. So this is the integral part, and this is the derivative part, and they are inverses. Let's put that in red. Those two operations are inverses of each other, which means they undo each other, much like squaring and screwing undo each other. So that's really huge. I guess my next step is to start giving you functions and asking you to predict their integrals. Because an integral is an antiderivative, we differentiate it. Usually I've been using the pattern where we take a function and we take its derivative and we take its derivative moving down like this. I'm going to ask you to take a function and find what would give a slope of the given function. So that means take the integral in order to go up like this. So let me give you an example. I'll say here's a function, and this function is constant, and let's say that it's 3. And we'll use the language of physics. This is position as, not position, I'm so sorry. This is velocity as a function of time. And if the velocity is 3 for this entire time, then I could ask you to predict how the position is changing. There are a lot of ways to do this, but one way to do it is to say, well, if we know the velocity is 3, then I know I need to draw a line here whose slope is 3 all the time. So I'm going to try doing that with purple. This is kind of crazy. And I'm going to put a line here that shows a slope of 3. That's not exactly a slope of 3, it looks like a slope of 1. But you understand the idea. Ooh, what if I force it to be a slope of 3 by telling you that that's what it is? Slope equals 3. There, now it looks like a slope of 3. Okay, so if this position versus time graph has a slope of 3 the whole time, then the velocity graph would be here. I'm trying to take the integral. Or integrate. I'm trying to integrate this function to get that function. Now, the way we looked at that was we said we're taking the area underneath this curve. There's the curve, and notice that as I go further and further to the right, I'm getting more and more area. That makes sense because as I'm graphing the integral, it's getting larger and larger and larger because as I'm going to the right, I'm getting more and more area, and so the integral has to increase, 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 increase. Now, what you don't know is you don't have any idea where this line starts. It could also have started from here. And as long as it increases, as I go to the right, I'm adding more and more and more contribution to the integral. As long as it increases at exactly the same rate, it is another possible integral of my function, as long as I write slope equals 3 again. So let's try to make this idea more concrete. I want to make a function for you. I'm going to say here's a function of x. I'm going back into the math language. I hope that doesn't bother you that I switch back and forth. You can ask me to explain it in the comments and I'll go through it again. And then I'm going to ask you to consider the integral of that function. Here's the function. This is the integral sign. And then I'm going to tell you to integrate over x. So I'm integrating this function as x goes on. Much like here I was integrating velocity as time went on, I'll be integrating this function as x goes on to the right. So here's the function 0. And the question is, what do I get if I integrate 0 forever over to the right? As a function of x, I'm adding more and more zeros to it. Well, maybe your first instinct is that you don't get anything adding a whole bunch of zeros. And that's reasonable unless you have infinite zeros, and then that's 12. But if you have just a certain number of zeros, as you're going to the right, adding more and more and more zeros, you're not going to get anything until you get all the way to infinity. But that takes a long time. So if you're not quite to infinity, it gets 0 for you. However, that's not to say that you've had 0 the whole time. What if you started at 7 and you added a whole bunch of zeros? You'd still have 7, right? So really, there's a fundamental uncertainty here, and you could call it initial conditions, or you could call it adding a constant. In math, they'll call it adding a constant because they don't know anything about anything. But in physics, we can call it initial conditions. Because that's real. That is what was happening before we started watching the experiment, or before we clicked our timer, etc. So the next thing that might be fun to integrate would be the function 1. What if I had a function that was 1 the whole time? So every time I go over in x by 1, I want to add 1 to my function. I'll see if I can give you an example of this over here. Let's see, how am I going to do this? Make it clear what we're talking about. I want to take the function 1, where this is y as a function of x, and it's 1 the whole time, and I want you to find the integral of this function. And trying to find the integral means that, well, let's see, if I'm adding 1 on all the time, let's shade in this area here. This is the area under the curve, and we're adding 1 every time we go over by 1. That means we're going to have a slope of, check it out, what's the slope? Slope must be 1. And what function has a slope of 1? Your favorite, y is x. So this is going to give us x. But there's a problem. It might not give us x, it might give us x plus 1. X plus 1. Or it might give us y is x plus 33. Or it might give us y is x minus 12. Right? All of these have the same slope because they're all parallel. They simply have a different y-intercept. And so we need to add a constant again. In fact, the initial conditions are going to be required every single time. If you're asking for an integral, you don't excuse me. You don't know the initial conditions. So let's make this a little bit more interesting. We've integrated 0, and we got 0 plus a constant. We've integrated 1, and we got x plus a constant. What if I integrate some constant? Let's call it d, maybe. If I integrate that constant, I'm just going to get a slope. I'll call your attention to this up here. I'm just going to get a slope of d times x plus a constant. I'm always going to have a constant. So clearly this value right here is the slope of this value right here. I guess that's a good check, because every time we look at this integral, we know that we should be able to differentiate it to get back over to here. So getting from that side to that side, we integrate, and getting from this side to that side, we differentiate. Because they're inverses of each other, we know that that should be able to go both directions. If I want to get x over here, what do I need to differentiate to get x as my result? Now you may be tempted to consider x squared, because you know when you differentiate it, we lose a power of x. Look here, as we're differentiating x plus c, the power of x was 1 here, and we lose a power of x, so we get x to the 0, which is equal to 1. So the x goes away. We're going to lose an x here, and so we're going to go to there, but this is not exactly right, because I'll remind you that this x squared differentiated is 2 times x. And then, of course, we have to add this c every time, right? So if I have a function 2x and I'm trying to find its integral, well, that's x squared plus c. But what if I just want the function x over here? I guess I can just divide both sides of this relationship by 2, and I'll find that the integral of x is x squared divided by 2. And again, I have to add a constant. Whoa, red line, this is getting a little bit messy in here. Clear that up. Okay, let's do another line. If I'm trying to find the integral of x squared, you want to guess? All right, guess. Okay, we're back on. This should be x to the third, but remember, when I say x to the third, if I differentiate that, I'm going to get 3x squared. So I need to divide that by 3 and then add my constant. Let's continue this same procedure on the next sheet. We will go to considering, I'll just write my headers back here again, f of x and the integral of f of x over x. And we continue. What if I'm trying to get x to the third? You start to see a pattern here. If I want to get x to the third, I'm going to need to put in x to the fourth, but I can't get x to the fourth. I'll get 4x to the fourth. So I don't want to do that. I need to divide by 4. Interesting. X to the third divided by okay, all right, now then we add c onto it, because every time we have to add this constant because we don't know the initial conditions. So let's write a general form here. If I'm looking for the integral of x to the n, why, that's going to be x to the n plus 1 divided by, what do I want here, n plus 1, yep, n plus 1, and then I have to add that stupid constant, which represents the fact that we have no idea what was going on when we started. As physicists, we really do know that, which is kind of the whole point. So this gets very, very exciting very quickly. I want to put it into the physics language over here, and I want to derive for you something that has probably been bugging you since your first year of physics. And here it is. If I have a function of time, and I look at the integral of that function of time over time, I'm going to do just a few problems. Instead of calling these constants c, I'm going to call them, I don't know, a, v, and t. So the integral of 0, first of all, is a constant, which I'll just call a. It's not any of the variables that we're using here. I'm just going to label it a. Just say what it, you know, what the heck. I can call it what I want. I can call it b, right? Couldn't I call it b? Yeah, I guess I could. And if I take a then, and I integrate a, then I'd get, well, I'd get a times the variable, right, which is t, plus another constant. And that's just going to be, well, let's just call that constant V0, just for the heck of it, right? Then if I take this function right here, a times t plus V0, if I integrate this sucker, I'm going to get, ooh, check this out. This is going to be, well, the V0 term is just going to be V0 times t, and this other term is going to be a times t squared divided by 2, and those guys have to be added together. Then I have to add on a constant, and I'm just going to call that x0. So if I I'm just going to write these just slightly in a different way. I'm going to write it as x0 plus v0 times t plus 1/2 a times t squared. Boom! This is the final position. We have simply derived the classic kinematic equation. That's a good place to stop. I want to mention one final thing about integration, and that's the idea of how we can actually get it done. So, if I have some function, and it's doing, I don't know, this or something, and I want to know, let's go back to the math language, y versus x, I want to know what the area is under here. Now, in math, the interest for looking at it this way is a very theoretical one. They want to understand how you can construct an integral. In physics, we could just say, in principle, we could know the area underneath that, and then we could use it for calculations. But it's a practical one for us, not a theoretical interest, but a practical interest. How do we get a computer to take a function and find the area underneath that curve? And so one way of doing it is by breaking each of this function, each chunk of this function, into a rectangle. And the idea is you break it into a rectangle of fixed width. All the rectangles are the same size, and the area of a rectangle is easily known. No problem, right? And so you just take the area of each of these rectangles and add them all up together to find the total area under the curve. These should be all the same size. So what we're going to do is we're going to call this delta x, and we can take the height of this function and multiply it by delta x at each of these points. But you see there's a problem. And the problem, because it's a problem, I'm going to draw it in red. The problem is these areas right here are not counted, right? And so then you say, oh shoot, we have a number for the integral that is too small. And it's too small by that amount right there. By the way, this method is called a Riemann sum. So we've got some error that's shown in red, but what if instead we take this function, and it looks something like that, I don't really care what, and then we make rectangles, but this time we make our rectangles and we measure from the right side of the interval rather than the left side of the interval. So the only remaining thing I wish to point out to you is that if we slice the curve area into very tiny intervals, then we will more precisely map the function. In fact, our friends in math tell us that the closer these intervals are together, the more accurately we can measure the integral. So, in math, they have a wonderful trick for this. They use limits to make sure that this interval goes to 0. They want the spacing to go to 0, but that means that we need to have, if the spacing actually reaches 0, how many of these intervals do we need to have, right? So we'd have to have infinite spacings, and each of them would have a space of 0 width. but we'll just multiply that by the height of the function. And that's what integration truly means. On a numerical level, if you program a computer, for instance, to do integration for you, you'll be taking each rectangle with a width of 0 and adding it to an infinite number of other rectangles that have each a width of 0, but the heights will all be mapped together. And in a computer, you will take a small width, and of course, the width of your area, the width of your rectangle, depends on how accurately you want to map the integral. And I've got a simulation I'll show you that allows you to play with changing widths in order to do integration. That's it for introduction to integration, and next up we'll do a practical video. How does integration and how does differentiation help us in physics?